Hello, everyone. Thank you for joining this data point session. My name is Ilya Katsov. I'm Vice President of Technology at Grid Dynamics. And today I will be talking about improving quality control processes in manufacturing and transportation using advanced analytics. So for this session, basically I will be focusing on two topics. The first one is predictive maintenance, what kind of techniques we can use to build predictive maintenance for industrial IoT data, and what are the basic and what are the advanced techniques and capabilities that we can use. And the second topic is automated anomaly detection, which basically extends some of the monitoring capabilities that I will be talking about in this first session. Again, we will talk about some tricks, some techniques that we use in practice doing projects around automated anomaly detection. And finally, I will spend some time talking about how a complete industrial IoT analytics solution can look like, including how predictive maintenance components and anomaly detection components and visual quality control components come together in one architecture, and how what are the best practices in building these types of solutions in manufacturing and transportation companies. So first, let's talk about predictive maintenance and how we can approach the problem of building a system or building a solution that provides predictive maintenance capabilities. First, let's start with a very basic setup, very basic approach that we hypothetically can use to build this type of capabilities. Let's assume that we have some device or some system or some physical process with a number of IoT sensors that produce different metrics, and we collect these metrics. It can be, in technical terms, it can be done in different ways. We will talk about it, but for now, let's just assume that we stream these metrics, for example, to some queues in the cloud, and then we can do some processing and visualization of this data. And the most basic thing that we can do, of course, is to build some dashboards that merely visualize these different event streams and numerical time series, so that the operation team can monitor these metrics and react if there are any abnormal behavior, if there are any anomalies in this sensor data. And this basic approach, of course, it's not realistic, it's more hypothetical, because in practice there are a number of reasons why it will not work. First of all, typically the number of sensors and the number of events and metric streams that are collected from real physical devices or assets can be very high. It can be, for example, thousands of metrics per complex machine or device, and it's not feasible to monitor all these metrics manually, or the cost of this monitoring will be prohibitively high. Second, this raw data can be difficult to interpret, and in many cases it requires a very high qualification to understand what these metrics really mean, and it complicates the monitoring process even more. And finally, this manual monitoring typically results in the slow response and resolution times, which creates high risks and potential high liability costs associated with resolution of these anomalies and so on. And because of these reasons, this basic approach is typically not feasible. But we can make a number of improvements to make it work in practice. So one basic improvement that typically makes sense to do in the beginning of a predictive maintenance or anomaly detection project is to build a system model that in many cases helps to reduce the dimensionality of the data, dimensionality of the metrics that we collect, and also isolate these metrics from at least some of the exogenous factors that influence system behavior. Typically, this type of system models, such as deterministic models that encode our prior knowledge about the system and what is important, and what parameters of the system do not change over time. So let me illustrate this with an example, and I will use this example going forward as a running case study. It is actually based on a real project, and I will use it to illustrate the concepts that I'm talking about. To be more specific. So, for example, let's consider the situation then there is the fuel distribution company that has some terminal fuel tank, and he uses for example, trucks or some other vehicles to deliver this fuel to gas stations or some other locations. And we collect metrics about the outflow of the fuel from the terminal tank to gas stations, and we also collect sensor data about the fuel level in the gas station tanks, and we collect information about the sales data. And it can be quite many metrics that we need to process and monitor, which might not be feasible to do manually. But what we can do, we can build a system that a system model that does a number of essentially simplifications and reductions to this raw data. For example, in this situation, it's in this particular project we used temperature corrections on top of these sensor metrics to remove fluctuations in the fuel level induced by outside temperature. And then we calculated a number of constant metrics that basically represented some sort of, like fuel conservation laws, if you will. For example, we know that the difference between that the fuel level should be essentially the difference between inflow and outflow of the fuel, so that should be no discrepancies ideally between the transactions registered on the terminal tank and what was actually delivered to the gas station tank. Also should not be discrepancy between fuel level and sales data. It should not be some changes in the fuel level at the gas station tank if there are no sales and there are no deliveries from the central location and so on. And this way we basically can convert these raw observations that are complicated with temperature, oscillations, and some other factors into metrics that presumably need to be constant or near zero. And of course, it's much easier to monitor these metrics rather than to monitor the raw data, and it's easier to apply more sophisticated statistical processing on top of these invariance compared to applying the statistical procedures on top of the raw sensor data. Then the second step that we can make to reduce the number of signals even further is to do signal importance analysis. And basically determine which signals are important and which signals are not important for monitoring purposes, and keep only important signals in the dashboards to reduce the monitoring effort even more. And to do this, the typical approach, the standard approach, is to build a classification model or supervised defect detection model that predicts some sort of like known anomalies based on labeled data that can be produced by operations teams. In some cases it is possible, in some cases it is not possible, but if we can build such a defect classification model, it can help us to significantly reduce the amount of data that we need, amount of metrics that we need to monitor. For example, going back to this scenario with the fuel distribution company, one correction that we needed to make in this project is to account for maintenance events at the gas stations, because in some cases these fuel tanks can be under maintenance, some sensors can be under maintenance, and the operation team that monitors this data, they created a labeled data set with different types of anomalies induced by these maintenance events. And it was possible in this case to build essentially a supervised model that could be used to predict these anomalies based on the observed events and maintenance events. And this model could be used to reduce the number of events that needs to be monitored because some of them are important, some of them are not important. And using this technique with anomaly prediction, we basically can reduce the amount of signals that we need to monitor, even further comparing to just usage of the system model. Then finally, what we can build even on top of that is to remove some anomalies that we do not consider significant. For example, if some devices are turned off or turned on by some maintenance reasons or something, then in many cases this just create noises that needs to be removed, and these noises actually are not of interest to the operation teams. The operation teams in some cases might be interested only in trends. And these type of anomalies can be removed using standard techniques such as PCA or autoencoders to reduce the number of, to clean up essentially the metrics that were prepared during using techniques that I just talked about in the previous stages, and produce cleaner signals that are easier to monitor. And all these techniques in combination basically help to reduce the number of signals, so that monitoring effort can also be reduced, and also they help to reduce insignificant anomalies that make the monitoring job easier compared to monitoring of the raw signals. And actually, some combination of these techniques, it can be in many cases sufficient to build reasonably good dashboards that can help to identify issues and take some preventive actions based on the monitored metrics, so that the whole solution is feasible and can be applied in practice. And this is not like, as you probably noticed, this is not like perfectly predictive solution, although we used some predictive techniques to clean up the signals. It's more relies on manual monitoring and building appropriate dashboards and data summaries to facilitate this monitoring. But in many cases, it's a reasonable solution that helps to provide predictive maintenance capabilities. And of course, some automation can be added on top of that. For example, some thresholds, some alerting thresholds can be configured based on this reduced number of relatively clean signals. But this is, of course, not the only possible approach that we can take. This is rather a simplistic approach to building this type of capabilities on top of IoT data. A more advanced solution can be obtained by essentially predicting the future state of the system, or predicting hidden state of the system, and then making some alerts that in turn converted into preventive actions based on this forecast, what will happen with the system next. So basically, let's say that we have some complex process and we collect a number of metrics from this process using different sensors, and we do all these reductions and noise removals as we just talked about. But then we need to build a model that essentially predicts the future state of the system, and more importantly, this model should correctly predict abnormal states. If the system is moving or process is moving into some abnormal state, then the system needs to predict it correctly. And this is a problem because in many practical scenarios, it's difficult to collect enough samples that cover all abnormal scenarios, and the problem of building or collecting this data becomes even more severe if we are using some complex high-capacity models that require a lot of samples to be trained. So it can be quite challenging to make this to collect this data and to build this type of models this way. And there are different techniques that can be used in practice to work around it. One technique that seems to seems to gain quite a lot of interest over the last couple of years is physics-informed learning, which basically is about augmenting the actual observations of the systems with the kind of calculated, simulated observations that are produced based on the physical model of the system, so that if we deal with some process for which we can build a good physical model, for example, using differential equations or something like that, then we can augment the actual observations with predictions produced by such a mathematical model, use this additional information or modify the loss function of the predictive model that we are training with these observations to improve the efficiency of model training. And it is generally a powerful tool for reducing data requirements that is a severe problem for building such predictive models. And in that case, if we use this technique and other similar techniques, it helps us to build models that predict the future state of the system, and it helps to predict abnormal situations and take some mitigation action based on this prediction at the right time. And generally, it helps to build more, of course, more powerful predictive maintenance solutions than just using the dashboard, as I previously talked about, right? But again, I would like to to comment that in practice there are I'm just talking about some best practices or some techniques that in our experience work well, but in practice there are a lot of different variations depending on a specific domain and type of manufacturing process. So in most cases these techniques are used in combinations, and there are many specific adjustments that are made in each particular case. So next, the third group of techniques that I wanted to talk about is anomaly detection. So in the previous two scenarios, we talked about building the dashboards and doing it efficiently so that different metrics can be monitored and scaled. Then we talked about predicting the future state of the system that can help to take preventive action on time. But another group of techniques that very frequently used in practice is, of course, anomaly detection. And in anomaly detection, we basically what we are trying to do, we are trying to build a model of normality, essentially, that captures the normal patterns of the system behavior, the manifold of the normal system behavior, and then if the observed data deviate from this manifold, then we essentially interpret these deviations as anomalies, and the magnitude of this deviation can be used to set severity levels for these anomalies. So basically the concept here is that, again, we have our process, we have sensors, we receive metrics from the sensors, we can do some pre-processing using system models that reduce the amount of data, and then we build a model that learns these regular patterns, and the difference between the actual observations and predictions made by this model are used to identify the anomalies, to score the anomalies, and then some alerts can be configured. And these alerts are then investigated by the operation team, and some troubleshooting action is taken. So this is a quite generic and quite powerful concept, but in practice there are many issues with this type of solutions, of course. One, the few typical problems that we face in practice with this solution are as follows. First one is that the individual signals, like individual metrics that we collect from the physical process, can be noisy, so it's can be difficult to reliably detect anomalies. Considering individual metrics in isolation, we need to basically assess the state of the whole system rather than assessing the states of individual components. Then if we are talking about a large system large installation, then it can be the case that new metrics or new devices can be added or removed, and we need to dynamically onboard new metrics and new devices to the system, and ideally this process should be automated. And finally, it's probably one of the most severe problems is that it's difficult to set the detection thresholds properly so that the system is fine-tuned and the alerts are not ignored by the operation teams, which is a quite common scenario, by the way. And in order to mitigate these issues, there are a number of techniques that are used in in building these anomaly detection models and some automation around it. The first technique that we frequently use in practice is topology-aware anomaly detection, so that these anomaly models, they do not score just individual metrics, but they take into account topology information, basically the graph that shows the relationships between different components in the system, and this information is used to assess the entire state of the system reliably, so that it's more robust against noises in individual metrics and individual signals. Then typically it's a good idea to think about automatic metric onboarding from the very beginning in the design of the systems, so that there are appropriate repositories of the models, there are appropriate tagging of different models for different types of sensors or different types of devices, and models can be reused if a new device, for example, of a known type is added, or model training for new types of devices is automated, and it can influence the design of the solution quite significantly. Then it's also important to provide good root cause analysis tools, so that operation teams can not only receive the alert, but they can trace these alerts to root causes in individual sensors, individual metrics, which is, of course, very important capability that needs to be designed properly. And finally, the last technique that can be used in many cases is training an additional alert or anomaly classification model on top of the unsupervised anomaly detection model based on the feedback provided by operation teams. And of course, this needs to be enabled by proper tooling, so that operation teams, they can provide some feedback on alerts, which alerts are important, which alerts are not. And this information can be used to train a supervised model that additionally classifies anomalies, and this way it can either prioritize or deprioritize certain types of alerts, and avoid the situations when we have a large number of alerts that eventually will be ignored by the operation teams. So to summarize, it's typically quite complicated ecosystem of different capabilities and different models, rather than just one basic anomaly detection model. It's not a straightforward problem. So to summarize, to illustrate what this anomaly detection process is, let's go back to our running example with the fuel distribution keys. So in that project, as we discussed, we started with consolidating data and building some system models that help to reduce the amount of signals. But then a number of different anomaly detection models were built to detect fuel theft, to detect malfunctioning meters, to detect leaks, to detect issues with the fuel flow, and in general, each of these anomalies required to build its own either model or some instance of a model combined with business rules to detect right type of anomalies. And basically, the platform that we built to support all these capabilities, it provided model repository, it provided all the tools needed to run multiple models in parallel, and provided capabilities to easily create and add new models on top of that, so that these different types of issues can be detected and reported properly. And of course, some of these models, they use the techniques such as topology, where anomaly detection that I previously mentioned. So to summarize the overall process of building the quality control solution that provides these different capabilities that we just talked about, at a high level, the strategy can be as follows. So we typically start with streams of IoT metrics, and for many purposes, we also need to get some information or continuously receive information about the topology of the system, how different sensors and different components are interrelated. Then we need to build data consolidation processes. We need to build a ML platform that allows to run multiple models and multiple data preparation, data pre-processing pipelines to implement the system models and these different techniques that we talked about. And then on top of that, we can start to build actual anomaly detection or predictive maintenance capabilities. For example, for building a predictive maintenance capabilities, as we talked, we typically need to build a stack of models that can include some deterministic system models. Then we might remove some anomalies out of the observed signals. Then we might need to build models that predict future state or future risks for the systems, and then we can build dashboards that can be used for monitoring of these future states and future risks of the system. Then anomaly detection is typically slightly different story. It's different capability that can be built separately. Again, we might need to build separate tools and models to detect anomalies, collect feedback, and provide insights into the observed anomalies and alerts. And finally, the visual quality control is a different capability. We did not talk about it, but for the sake of completeness, I just want to mention that it can share the same infrastructure, the same platform to collect not only numerical or time series data, but collect, for example, images. Then it's important to provide labeling tools, provide the capabilities for training both supervised and unsupervised defect detection models. And these models then for scoring purposes are typically deployed on edge devices to perform real-time serving. And this is basically how we can approach the problem of building a complete quality control solution at a high level. All right, so that's pretty much it. Thank you for attending this session. And if you have any questions, I will be happy to answer. Thank you.